Good, whatever time it is that you're watching this.
It is 6:26 in the evening when we made it. It is raining and there is a train literally going by right now, and it's super picturesque and cool. I'm enjoying the view.
Oh my.
Mr. Bobby doesn't like it when I talk about my view. Like he's jealous.
No, because I just live in a normal house, so I can't help it. I don't have the view of the top of downtown Little Rock. So
All right, today we're talking about 4.6 independent events and unions of events. Our learning objective today is to calculate probabilities for independent events and for the union of two events. Our learning objective and our topic sound very similar today. How about some essential knowledge?
that's a lot of essential knowledge.
It is a lot of essential knowledge, and we're actually going to go through it. Miss Robbie will maybe Mr. Bobby eyes it for us.
Okay.
Events A and B are independent if and only if knowing whether event A has occurred or will occur does not change the probability that event B will occur.
So just because one thing happened doesn't mean I know anything about what's going to happen next.
Right.
Sounds like The Walking Dead or something.
Right.
Is that still a thing? I don't even watch that anymore.
Yeah, I feel like they're maybe still making them.
Yeah, I don't know. I used to watch.
I feel like I've watched everything that's out there. Anyway, I put an example on this one because this concept of independent really confuses people. So think about tossing one coin and then tossing another coin. Like what happens when I toss the first coin is in no way dependent on, or excuse me, what happens with the second coin is in no way dependent on the first toss of the coin, okay? So they would be independent of each other. So that's kind of what you want to think about. Like if they're independent, then one does not rely on the other. One of these things is not like the other. Okay, next, events. If and only if events A and B are independent, then the probability of A given B is the same thing as the probability of A. And the probability of B given A is the same thing as probability of B. And the intersection of those two events, remember this is when we use the word and, is just the product of those two. You want to talk about that?
Yeah. Well, I think we're going to get a little better once we get into an example. I think it'll be a little clearer when we actually do it. So,
but I think you can even make sense out of this, right? If the two events are independent of each other, then even given B, it shouldn't change the probability of A. Right. And even given A, it shouldn't change the probability of B because they shouldn't be relying on each other. And then, yeah, we're going to talk about this multiplication rule kind of coming through.
Multiplication one, that's if you think back to when we were doing the Coke versus Pepsi, we had a big debate about
do I add or do I multiply?
Yeah, it was 1/2 and 1/2 and 1/2, or 1/2 times 1/2, 1 times
right.
1/2. It's actually multiplication.
Yeah.
Okay. But we'll come back to the Coke Pepsi a little bit later too.
Yeah. So the probability that event A or event B or both will occur is a probability of the union of A and B, denoted a union B. So remember, or is union, like a U, and is intersection, like an A. So this is just a reiteration of something that we already talked about. And then one more time for what we talked about in the last video, the addition rule states that the probability of A and B or both will occur is equal to the probability of A plus B minus the intersection of A and B, right? So that's we looked at the tables and we said this one's happening twice, so we have to take one away. Remember all of that? Yeah, keep thinking about that, okay? All right, imagine we're gonna play a game, and this is embarrassing to admit. Neither Mr. Bobby nor I have a deck of cards at our current location. I have some at school. He has some at his second house because he's fancy. He has two.
If you saw my second house, it's a fishing cabin. It's nothing special. But
I only have one house. I'm just saying. Well, I'm not that fancy. Rules of the game. You're going to have 5 cards total. Do you want to show us the 5 cards that you got? Ooh, 5.
1,
Slip
2,
paper.
3, 4, 5. Okay, it's the Arkadelphia Printing Company. Slips.
Nice. Okay,
Yeah.
so what we're going to do is we're going to say 2 of those pieces of paper are aces and 3 of those pieces of paper are kings.
And they are, in fact, if you notice right here, I wrote an A on that one and a K on that one for king.
Yeah.
So that's our playing cards. That's our fake playing cards.
Okay, so here's what we're going to do. The player's going to choose, and if we were together, we would totally be playing right now. The player chooses their first card, records the result, and then chooses the second card without replacement. Without replacement. Okay, so we're not going to put the first card back in because this totally changes our probabilities and outcomes, right? So, Mr. Bobby, if I'm not replacing it, are they independent or are they dependent? Is my second pull dependent on what happened the first time?
Yes, it does, because the first time I have a certain probability of getting a king. For example, there's 3 kings out of 5, so I've got 3 out of 5 or 0.6 probability of getting a king. After I draw a king, it changes. It's a different number, right? So I can't assume it stays the same. That's what it means.
Yeah, I kind of think about independent versus dependent. I always think about, is the denominator changing? Because if the denominator is changing, then the second version is dependent on what happened the first time, right? So there were 5 cards, and then we pulled one. We're not replacing it. They're going to have 4 cards. So my denominator changes when I think about, okay, there's 2 out of 5 cards, and then there's 1 out of 4 cards or something like that. There's dependence there on that second pull, on the first pull, okay? All right, so the player wins if they get a pair of aces or a pair of kings.
So I got to write it down, right? So I'm getting my iPad ready to go. Sorry.
Yeah, it's okay. So here's where the wording gets sticky. You have to really think about what's being asked here. So to win, you need an ace and then another ace. Or you need a king and another king. So in this problem, there's ands and ors. And remember, we talked about in a previous video how the word and the word or is really specific in mathematics. Or means we're going to add some stuff together, or in probability, excuse me. Or means we're going to add some stuff together, and means we're looking for when things happen at the same time, okay? And we're going to multiply. So or, add, and we're going to multiply. That's important. Okay, so let's play.
All right, so I'm going to pick one at random, and I got a king. So hold on, I got to get my annotation thing up here. Oh my gosh, I'm on the wrong color.
And it's Wednesday, so you darn well better write in pink.
I am writing in pink. All right, so I got a king, and I'm going to put it over here because my cards are over here. Okay, because I'm not replacing it. So I'm going to pick another one, and I win. I got another king.
Ooh, winner! Winner!
And that's a chicken dinner right there.
Chicken dinner!
Okay, so now what? Play it again?
I don't know why I'm so weird.
You are wound up. All right, I start with another king. How many times I got to play this?
I don't know, just a few times. We're trying to decide, like, what's the probability that you win this game? Ace. Loser. Yeah, so what we're trying to do here is we're using a simulation to try to say, like, what's the probability of winning? Okay, so we just had Mr. Bobby going through the motions here of playing some rounds and trying to get some idea of how often you win. Okay, so he just had a win and then a lose and then a lose. Now, he's just doing samples right now, right? So how many samples do we feel like we need? Well, in statistics, we generally think, okay, we've got to have at least 30. 30 is kind of our magic number in statistics.
I'm not playing this game 30 times.
But because we're not all playing together, and that is not fair to ask Mr. Bobby to do that, we're not going to make him go to 30. right? That's crazy sauce. But also know that our results that we get here when it's just us doing this, probably not going to be great. Remember that probability model where I had to fake shoot the ball like 100 times before you really started getting a good idea? Okay, we can't do that here because y'all don't want to watch a video that's 45 minutes of Mr. Bobby picking cards. All right, so let's make him stop. He's going to stop now, and because I'm done rambling.
Okay.
So how many games did you play? That was pretty
I
quick.
got 6. I got through 6 games, and I won 2
Okay.
and lost. So I have a probability of 1 out of 3 or 0.33 repeating.
Right. Okay. So our simulated probability of winning is 0.33 or 1/3. Okay. So I want us to determine the actual probability of winning, the actual probability of winning. So in order to do this kind of probability, we're going to use a tree. Okay. So think about what we said. There's ways to win and ways to lose. So let's just think about our ways to win. How can we win again, Mr. Bobby?
2 kings.
Okay, so we pull a king and a king. Okay, so we're going to not go to the tree yet. I just want to talk this out a little bit. King and a king. What's the probability that I pull the first king?
Well, I talked about that earlier. There were 3 of them in there, so it was 0.6 with the probability of me getting a king.
Okay, so there's 3 out of 5 that he gets a king. Okay, now he's got to pull another king. He's got to pull another king. So what's the probability that he pulls the second king?
And I'm going to call it, can I call it K1 for king 1?
That makes sense, yeah.
Yeah, and then the probability of me getting king 2, well, there's no longer 5 cards. There's only 4 cards left. And I've taken 1 away. So that would leave only 2 left. So that would be 2 out of 4 or 0.5.
Yeah.
And you take 0.6. I'm sorry.
Now, these are 2 different probabilities here. The first one is a probability for first king. The second one is the probability for only second king, right? What's the probability of king, king?
Well, would I multiply those 2? You were talking about.
That's right. Is it king and king, or is it king or king? Feels like an and, right? Got to have a king and a king.
Yep.
So I feel like we multiply. Now, this isn't the only way, and I'm not going to have him do all the math now because we're going to do it on the next slide, but this isn't the only way I could win, right? Or I could have an ace and an ace. So what's the probability that I pull the first ace?
There were 2 out of 5.
Okay, so I pull the first ace. After I pull the first ace, what's the probability that I pull a second ace?
Well, let's see, A2, there's only 1 left because I took the 1 of the 2. So there's only 1 out of 4 left.
Right. And we got a situation here, we got to have ace and ace, ace and ace. Now, this is a little confusing. And so what we generally do when we start doing these like dependent events where we have to take into consideration one thing and then a second thing where they're dependent on each other is we make a probability tree. So we're going to look at a probability tree here. Okay. So let me see here, clear the screen and switch slides. There we go. Okay. So this is called a tree diagram. It calculates our theoretical probability. Now, remember, before we get into this, that our very small simulation, we kind of think our probability is 1/3, 1 out of 3, or 0.3 repeating. Okay, that's our guesstimate from our simulation. So, are you ready?
Yep.
So, thinking about this, the probability that our first card is an ace. So we're gonna play the game like our first card is an ace. What is the probability that our first card is an ace? Well, there were 2 aces out of 5 cards. Now, from here, 2 events can happen. After I pull first ace, I can either now pull a king or I can pull an ace. If I pull a second ace, remember, I've pulled 1, I've not replaced it. My denominator changed, it's dependent. And, oh, I'm sorry. My brain did this totally different when I animated. Let me switch back here. So probability of pulling a king is 3 out of 5. And every time we do this, guys, you want to think about like 100% of the possibilities. Okay, so 2/5 plus 3/5 is 5/5. There's every bit of the probability, right? Or every bit of every card. Okay, so 1 out of 4 is that second ace that we pulled. We talked about that second ace. But there's another option that could have happened. I pull the first ace. I've got 4 cards left. One of them's an ace, 3 of them are kings. So the probability of pulling a king instead of an ace the second round is 3 out of 4. Now remember the remaining cards. So I should be able to add these two together and get 1 again, because this is everything that should have happened.
That's a second action.
In this Choose Your Own Adventure. Did you guys ever read the Choose Your Own
Oh,
Adventure
I
book?
love this. They play games like that now. I think like they're games.
Oh yeah, because everything's highly
Everything's gamified now.
instead of like, if you want to go left down the road, turn
Go
to
to page 57. Yeah, that back in the old days when we actually had books, we had to actually had to read our little adventure stories.
Yeah. All right. So our probability of ace, because we're talking and here, dependent and events, would be, oh my God, I did it again. I went straight down the road because my brain was like, yeah, I'll totally go straight down the road. Back up with me. You're going kings here. Okay. So I have 3 out of 5 are kings. So my chance of pulling a king is 3 out of 5. Okay. I pulled the king. Now I've got 4 cards. 2 of them are kings, 2 of them are aces. So 2 out of 4, I get a king. 2 out of 4, I get an ace. Got a 50-50 chance here. Okay. In this Choose Your Own Adventure situation where I started with a king, I should again add to 1 because I should have everything that's left. I should consider it. Sometimes people get confused because they think this whole column should add to 1. But this is 2 Choose Your Own Adventure situations. Okay. All right. Now we're going to go ace, ace. So this is first is an ace and second is an ace, and we multiply. So we multiply, we get 2 out of 20 or 0.1. That means there's a 10% chance I'm going to win on my aces. A 1 in 10 chance I'm going to win on my aces. So good job, Mr. Bobby, because didn't you win on an ace in 6 tries?
I had a double ace. Yeah, I might have.
Yeah. What's the probability of getting an ace and then a king? An ace and then a king. So we got an and word again. We multiply 2/5 and 3/4, and we get 6/20 or 0.3. So 3 in 10 chance I'm going to lose on a first pull of an ace. If I pull an ace, there's 3 in 10 chance I'm going to lose. Okay. All right. I pull a king and a king. King and a king. King and an ace. King and an ace. So 3/5 times 3/4, we get 0.3 again. King and a king. King and a king. I win. How often am I going to win on a king? I got a 30% chance I'm going to win on a king. So 3 out of 10 times we would expect to win on a king. 1 out of 10 times we would expect to win on an ace. How many times do we expect to win if it's kings or aces that win, Mr. Robbie?
We combine those 2 red ones and add them up to 40%. So I wasn't far off. I had 33 or 0.33, and that was 0.4, and I wasn't going to get because I only did 6. I'd have to do more trials. So I was relatively close.
Yes,
pretty
good with our teeny little sample size. Couple things. This last one, you can add the whole column because this is a probability of every event in the situation. The probability of every event possible in the situation should add to 1. Okay, should add to 1. And then the notation you would write here is winning would be the probability of aces or the probability of kings. Ace, ace, king, king. The or is important because even though we multiplied in the tree because it was and, this is an or situation. So we've got the 0.10 plus the 0.30. So we would say, okay, there's a 40% chance we're going to win. 4 out of 10 times we would expect to win. Does that make sense? Are we good?
I'm good.
Everybody good? I hope you're good because you can't tell me. Okay. So, what is the probability that the first card was a king given the person won the game?
All right, so now we know we're only looking at the winners.
Mm-hmm.
And so we have to figure out, now let's go back and look at those formulas.
So the given, and I don't have it here, being winner, but remember it was a 40% chance you were going to win, right? 40% chance you were going to win. What was the probability that you were going to win off of pulling a king? Wow.
0.3.
Right. So there it is.
So we're going to take that 0.3. So you have a 30% chance of winning with the king.
Mm-hmm.
A 40% chance of winning, period. So we're going to divide those two, 0.3 divided by 0.4.
Yeah.
And that would give me 0.75. So if I knew you were a winner, I would know that 75% of the time you had drawn a king first.
Right. Exactly right.
You're
Exactly right. You're brilliant, Mr. Bobby. Okay, you're gonna have to draw.
All right, got me here.
Okay. A book problem. A computer company makes desktops, laptop, and tablet computers at factories in 2 states, California and Texas. The California factory produces 40% of the company's computers, and the Texas factory makes the rest. Of the computers made in California, 25% are desktops, 30% are laptops, and the rest are tablets. Of those made in Texas, 10% are desktops, 20% are laptops, and the rest are tablets. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from the distribution center and observe where it is made and whether it is a desktop, a laptop, or a tablet. So the first question is, find the probability that the computer is a tablet.
Okay, so we have the first decision to make is, because we have different probabilities for each state, desktops or tablets. There's desktop, laptops, right? Oh, and tablets. There's 3. Yeah. Okay. The first decision we got to make is it going to be made in California? Can I do just CA?
Yeah.
Or Texas? Okay, TX.
So why would we not go the other direction, Mr. Bobby? Why would we not do desktops, laptops, and tablets, like 3? Why do we start with the states?
Well, partially because it was first, but also because each state had different probabilities for the other, for the percentage of each type of computer.
Right.
Okay. So California's percentages of different types of computers were not the same as those in Texas. Okay. So what we do know is that California produces 40% chance. So this is the California branch is 0.4. I have a 40% chance of going down that branch. And if California is 40, the complement of 40 is 60. Okay. And then once I've decided I'm going to California or Texas, then I'm going to branch off into 3 different branches: desktops, laptops, or tablets. And in this problem, they're not giving you all of them, but they're assuming you know that they're supposed to add up to 100. So if you don't have a big major beef with this, I'm going to use a different color for the second decision.
I think that's wonderful. People like a good
colorful tree diagram.
A good green.
Yeah. So this one would be the top one. The first thing they give me was the types of desktops, right? And the probability of getting a desktop for after you've been in California was what, 25?
Mm-hmm.
So that was 0.25. And then the next one is what was laptops?
Yep.
And what was its probability? 30? Who even
Yep.
buys desktops anymore? All right, now I need to figure out tablets. Well, how much have I already used?
55.
25, 55. So my complement to that would be 45.
Right. Now, remember, we talked in the previous problem about these little trees. They make 100% themselves. Okay. So that's how we know, like, and it's a little, makes a little more sense in this reading, but sometimes that gets a little confusing. But yes, each little branch in the middle gets its own 100%.
So that green branch has to be 100% as well, just like the pink branch had to be 100%. And this blue branch has to also be 100%. So desktops in Texas were 10%. What was it? 20% for the laptops. That means I've used up 30% total. And so that leaves me with 70% left, which is what the tablets are.
Now,
Okay.
I'm going to come back to our original question. Our original question here, because he's just given you everything that was given in the prompt in tree form. Okay. So the first question based off of that information now is find the probability that the computer is a tablet. So we want every situation where it's possible that it was a tablet. Now, when you do this for me in an open response question, I'm going to want you to fill out the whole tree. So you're going to be really tempted at this point to just say California tablet probability, Texas tablet probability, okay? But I want you to go ahead and fill out the entire tree for every situation that could possibly occur, and then check it and make sure you get 100% so that you know you did it right.
Yeah. So like right here, let me do this one in purple. If I were going to do this one, that the chances of me ending out there would be 0.12. Right?
Yeah.
What's the where did the 0.12 come from?
So California and laptop. California and laptop means we're going to multiply 0.4 times 0.3. We're going to get 0.12. So 12% of the laptops were from California. Is that what you're saying?
No, I'm saying 12% of all of them, all of the computers are California laptops. Okay. So, and actually I picked the wrong one. I need this number right here.
Yep.
And this number right here. This number is 0.42. I don't have, so what I'm doing is 0.6 times 0.7. Here I got to do 0.4 times 0.45. Do you know what that number is? Have you punched that out already?
It is 0.18. 0.4 times 0.45. 0.18, yes.
Yeah. Okay, so I want to take the 0.18 plus the 0.42, and that's going to give me 6.6. All right. So the first numbers in green were the probability on each branch. I probably shouldn't have put it at the end like I did. That was probably not the best alignment. I should put them like within the branches. But the chances of me ending in each of those three branches is what I have circled there in purple at the end. And I would do the other three. Okay. 0.12, 0.06, and whatever.
Yep. So the next one says, if we select 4 computers at random from the distribution center with replacement, what is the probability that at least one of the computers is a tablet? So in this case, we really want to think about what's the probability that there's at least one tablet? So if we're thinking about the probability that there's at least one tablet, probably the easiest way to think about that is, what's the probability that there's no tablet?
You're
Okay.
doing the compliment thing on me again.
Compliment.
Don't you look pretty?
Thanks. I wore my pink, 2 colors of pink just for you.
That looks purplish to me, but nice try.
You do this every time. Like, my pink is never pink enough for you.
Well, this is pink right here, man.
Okay, so the probability of it being a tablet is 60%. So the probability of it not being a tablet is 40%. Okay? Now remember, we're going to pick 4. We're going to pick 4 of these. So we're going to do 40 times 0.40 times 0.40 times 0.40 for all 4 of those. And then we're going to do 1 minus that, right? Because we want the complement. Because what we're really looking for is the probability that at least 1 is a tablet. But the easiest way to do that is to look at the complement. Okay, next question. I just put the answer up. Given that a tablet computer is selected, a tablet computer is selected. So you're seeing tablet on the tree right now. What is the probability that it was made in California?
So you're guaranteeing me that we have a tablet here. Okay. So we're only worried about this guy and this guy. Right. So how many were made in California? 18%, right? And what's the total number of tablets? 60%. So 0.18 divided by 0.6 gives whatever she has. I don't know if you have a number figure there.
I think I do.
Okay.
30%. Yeah. So there you go with a tree diagram. It's beautiful. Mr. Bobby is a freaking artist.
I feel real like I should use more colors, but I like the pink.
Okay, so we've got some really think hard ideas in this particular unit. We've got the tree diagram, and then we've got the concept of independence, and there's this concept of at least 1 being the complement of 1 minus none. Okay, so there's a whole Khan Academy about at least 1. So when you see the Khan Academy on at least 1, every single time, if you'll do this complement idea of 1 minus none, it will make more sense to you, I promise. Okay, so you actually have 2 days to work on this assignment. Well, this day and then tomorrow as well. There is a 4.6 tree diagram assignment, and I attached the answers with the trees because you will struggle. Okay, so I want you to struggle through it. Then I want you to look at the actual answer, and then I want you to make corrections to your work. And then I want you to submit that, okay? So I'm going to be actually looking for corrections to your wrong work, because I don't think y'all are gonna get it right the first time. So I'm gonna say it again, what my expectations are. Try it, correct it, turn in the paper that shows your corrections, okay? And then you have 4 Khan Academies for this assignment. Struggle through it, my dears, struggle through it because it is tough.
Don't wait till the last minute. Bye.
Yeah, don't wait till the last minute.